All right, welcome to video 2 of Strategies for Optimization. First thing we're going to do is we are going to fabricate a box, and then we want to maximize the volume of that box. And so I've drawn a little sketch over to the side here of exactly what it is we're looking at. We're going to take a piece of material, 20 by 25 centimeters. We're going to cut out squares from the corners. We're going to fold up the sides. We're going to have the box pictured below. And the height of the box will be x, and the sides will be 20 minus 2x and 25 minus 2x. That gives us a volume of length times width times height, looking right here at that equation, and multiplying it out, we get a cubic. So we want to maximize this volume. What we are going to do is find the derivative, which is going to be 12x squared minus 180x plus 500. We're going to go back and we're going to insert an equal sign right in there. And using the quadratic formula, because why not? What we discover is that the derivative will be equal to 0 when x is 3.681 centimeters and when x is 11.317 centimeters. These are our critical points. Well, a little inspection shows us that we can't cut 11.317 centimeters out of both corners of a 20 centimeter wide piece of paper, and therefore the only possibility is 3.681. A couple ways to check and make sure that this is a maximum. Very important that on every one of these problems we check to make sure that it's a maximum, because it could be a minimum, could be an inflection point. It is just a critical point at this time. So we could take the second derivative, or we could just calculate v of cutout 0, v of cutout 10, and what we discover is that those are both 0, whereas v of 3.681 actually gives us a volume of 820.528 cubic. Well, I said centimeters. My paper says inches, doesn't really matter. So there is our optimal situation, which is that when we cut out 3.681 units from each corner, squares, we will maximize our volume. Next example, example 4, we are designing a can, and what we want to do is minimize the material. So we're minimizing surface area. Surface area of a can is the two tops, top and bottom, and the side. So you may remember 2 pi r squared plus 2 pi r h, area of the top and bottom plus area of the sides. We've got a bit of a problem here, is that we have two variables and can't really do anything with that. So we need to get rid of one of the variables. Well, here's what else we know. We know that the volume of this can is 1,000 cubic centimeters, and that the volume of a right cylinder is pi r squared h. So when we set that to 1,000 cubic centimeters, we know that the height is now a function of the radius. We can plug that into surface area, and now we have surface area only as a function of radius. Doing a little simplifying, we cross off one of the r's, we cross off the pi, and we get 2 pi r squared plus 2,000 over r. So we're going to go ahead and take the derivative of that. The derivative of surface area as a function of r is 4 pi r minus 2,000 over r squared. We're going to set that equal to 0. And what we discover is that R must be approximately 5.419 centimeters. And again, a couple things we could do. We don't really have an idea of what our minimum and maximum are necessarily on this. So we're going to go ahead and do the second derivative of this. And when we take the second derivative, we get 4 pi plus 4,000 over r cubed. Well, clearly this is greater than 0 for all possible radii, since radius has to be positive. And that means that this must, in fact, be an absolute minimum. So we're going to make the radius of our can 5.419. We can therefore find out that the height of our can by plugging back into here must be 10.839. And we have minimized. I said minimum. Did I say minimum? I think I might have said maximum earlier. Second derivative is greater than 0. That is a minimum, which is what we're looking for. I threw out the wrong word. So there's the dimensions of our minimum can. All right. Thanks for watching. We'll be back with economic examples about profit, revenue, and cost in our third video.